Right now, at this very moment, you are moving through space at 2.1 million kilometers per hour. Not because of Earth's rotation around its axis, not because of our planet's orbit around the Sun, not even because our solar system is circling the galactic center. No, this is something else entirely. You're being pulled. Something out there in the darkness, something so massive, so incomprehensibly huge that it's dragging our entire galaxy, along with millions of others, toward it at incredible speed. We call it the Great Attractor. And here's what terrifies astronomers. We can't see it. We can only measure its effects. We can feel its gravitational fingers reaching across hundreds of millions of light years, pulling us inexorably forward. For decades, scientists tried to locate what was pulling us. They calculated trajectories, mapped velocities, measured distances. When they finally pointed their most powerful telescopes in the right direction, what they found was nothing. Just an empty zone in space. A cosmic blind spot created by our own galaxy's dusty disk. But the mathematics don't lie. Something is there. Something enormous. Something that makes our Milky Way look like a grain of sand on an infinite beach. And it's not alone. Beyond the Great Attractor lies something even larger, the Shapley Supercluster. 10 times more massive than anything in our local neighborhood. And beyond that, we don't know. The universe might have structure on scales we haven't even begun to comprehend. Structures so vast they challenge our fundamental understanding of cosmology itself. What I'm about to show you will fundamentally change how you understand the universe and our place in it, because we're not just drifting through space randomly, following our own independent path. We're being pulled toward a destination we may never escape, or rather, we may never reach. We're falling through invisible gravitational rivers that have been flowing for 13.8 billion years, since the moment the universe began. This is the story of humanity's discovery of the largest structures in the universe. The story of how we learned we're not in control of our cosmic destiny. The story of what it means to be a conscious, thinking observer in a universe governed by forces we cannot see, cannot touch, but can remarkably understand. Before we dive into the deep end of cosmic mysteries, I want you to do something for me. Stand up for a moment. Go ahead, pause the video if you need to. Feel the ground beneath your feet. You feel stationary, don't you? Stable, secure, at rest. You're not. Right now, at this exact second, you're spinning at 1,670 kilometers per hour due to Earth's rotation. That's faster than the speed of sound. If Earth suddenly stopped rotating, if the planet just locked in place, you'd be launched eastward at supersonic speeds, tumbling through the atmosphere like a ragdoll. The only reason you don't feel this motion is because everything around you, the air, the ground, the buildings, is moving with you. But Earth's rotation is just the beginning of your cosmic journey. Our planet is also orbiting the Sun at 107,000 kilometers per hour. That's fast enough to cross the entire United States in about 3 minutes. Fast enough to circle Earth's equator in just over 2 minutes. We complete one full orbit every 365.25 days, traveling 940 million kilometers through space. And we never feel it because, again, everything travels together. The moon, our atmosphere, everything. The entire solar system, sun, 8 planets, hundreds of moons, millions of asteroids, billions of comets is moving around the galactic center at 720,000 kilometers per hour. We're located about 26,000 light-years from the Milky Way center, on the inner edge of the Orion Arm, a minor spiral arm. At this distance, we complete one full orbit every 230 million years. The last time we were in this exact position in the galaxy, dinosaurs were just beginning to evolve on Earth. The next time we return here, dinosaurs will have been extinct for 165 million years again. And the Milky Way itself, our entire galaxy, all 200 to 400 billion stars, is hurtling through space at about 2.1 million kilometers per hour. Toward what? That simple question launched one of the greatest mysteries in modern astronomy, and the answer revealed something profound about the structure of the universe itself, something that changed our understanding of cosmic geography, of where we are and where we're going. If you're ready to have everything you thought you knew about space fundamentally challenged, hit that like button right now. It helps the algorithm share this video with more people who need to know where we're really going. And subscribe, because we're building a community of people who aren't afraid to ask the uncomfortable questions about reality. Questions like, are we in control of where we're going? Or are we just passengers on a cosmic journey we never chose, flowing along predetermined channels carved by gravity over billions of years? Now, let's begin at the beginning. Let's travel back to 1964, when humanity first got a hint that something strange was happening with our motion through space. To understand the Great Attractor, we first need to understand what the universe should look like. According to the cosmological principle, one of the foundations of modern cosmology, the universe should be homogeneous and isotropic on large scales. Let me break that down. Homogeneous means the universe looks the same at all locations. If you could teleport to a random spot 5 billion light-years away, you'd find roughly the same density of galaxies, the same types of structures, the same physical laws. Isotropic means the universe looks the same in all directions. Look north, look south, look east, look west. You should see statistically similar distributions of galaxies. This principle isn't just a philosophical assumption. It's based on observations. When we look at the universe on very large scales averaging over regions, a billion light-years across, it does appear uniform. The cosmic microwave background radiation, the afterglow of the Big Bang, is uniform to about 1 part in 100,000 across the entire sky. But here's the thing. On smaller scales, and by smaller I mean hundreds of millions of light-years, the universe is not uniform. Galaxies clump into groups, groups cluster into clusters, clusters connect into superclusters, and superclusters arrange themselves into a vast cosmic web of filaments and sheets surrounding enormous voids. This structure isn't random. It reflects the universe's history, how quantum fluctuations in the first fraction of a second after the Big Bang got stretched to cosmic scales and then amplified by gravity over billions of years. According to our models, this structure should be statistically random. Yes, there are concentrations of galaxies here and voids there, that there shouldn't be any special directions, no preferred orientations, no cosmic flows carrying entire superclusters in specific directions, except there are. And the discovery of these flows, particularly our own motion toward the Great Attractor, revealed that our local region of the universe has structure on scales far larger than anyone expected, structure that took decades to map, required observations across the entire electromagnetic spectrum, and fundamentally changed our cosmic address. But I'm getting ahead of myself. Let's go back to the beginning, to 1964, when 2 engineers at Bell Labs made a discovery that would eventually lead us to the Great Attractor. The story of the Great Attractor actually begins with a discovery that had nothing to do with it. In 1964, Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, trying to eliminate noise from a sensitive microwave antenna. No matter what they did, no matter how they oriented the antenna, no matter what time of day or night, they detected a faint microwave signal coming from all directions. At first, they thought it was pigeon droppings. I'm not joking. They literally cleaned pigeon poop off the antenna, thinking that was the source of the noise. It wasn't. The signal persisted. What they discovered, though they didn't realize it immediately, was the cosmic microwave background radiation, the afterglow of the Big Bang itself. This discovery revolutionized cosmology, provided the strongest evidence for the Big Bang theory, and earned them the Nobel Prize in Physics in 1978. But hidden in their data was something strange, something that would puzzle astronomers for years. The cosmic microwave background isn't perfectly uniform. If you map it across the entire sky, you find that it's slightly hotter in one direction toward the constellation Leo, and slightly cooler in the opposite direction, toward Aquarius. This pattern is called a dipole because it has 2 poles, hot and cold. At first, this made perfect sense. It's a Doppler effect. When you move through radiation, the radiation ahead of you gets blue-shifted, appears hotter, and the radiation behind you gets red-shifted, appears cooler. It's the same principle that makes a car's engine sound higher-pitched as it approaches you, and lower-pitched as it drives away. So astronomers calculated Earth's motion through the CMB. They started by accounting for Earth's orbit around the Sun, that's 107,000 kilometers per hour toward or away from different directions depending on the time of year. Then they accounted for the Sun's motion around the galactic center, 720,000 kilometers per hour toward the constellation Cygnus. Then they accounted for any peculiar motion of the Sun relative to nearby stars. But even after removing all these known motions, there was still a dipole, a big one. The residual dipole indicated that the Milky Way itself, our entire galaxy, was moving at roughly 600 kilometers per second, that's 2.16 million kilometers per hour. toward a particular direction in the sky. The coordinates: roughly right ascension 10 hours 20 meters, declination -30. That's in the general direction of the constellations Hydra and Centaurus. This was strange. Very strange. The cosmic microwave background represents the average rest frame of the universe. It's like the universe's own definition of standing still. Galaxies should be, on average, at rest relative to the CMB. Some galaxies might be moving a bit in one direction, others moving a bit in another direction, but these motions should be random and should average out. Our galaxy's motion 600 kilometers per second in a specific direction was not random. It was directed, purposeful, as if something out there was pulling us. But what? And where? Throughout the 1970s, this remained a puzzle. Astronomers knew we were moving, but they didn't know why. The answer would come from a different line of research, measuring the velocities of nearby galaxies. In 1977, a group of astronomers began a systematic survey to measure the velocities of nearby galaxies. This team, sometimes called the Seven Samurai in the astronomical literature, for their decisive contributions included Donald Lyndon Bell, Roger Davies, Sandor Faber, David Burstein, Robert Davies, Alan Dressler, and Gary Wegner. Their goal was conceptually simple: measure how fast nearby galaxies are moving through space. But the execution was extraordinarily difficult. Here's the problem: when you look at a distant galaxy and measure its spectrum, you can easily determine its redshift, how much its light is stretched toward longer wavelengths. This redshift has two components. First, there's the cosmological redshift caused by the expansion of space itself. As space expands, it stretches the light traveling through it. The farther away a galaxy is, the more space has expanded between us and it, and the larger the redshift. But second, galaxies also have peculiar velocities, their actual motion through space due to gravitational interactions with nearby structures. These peculiar velocities also create Doppler shifts that add to or subtract from the cosmological redshift. The problem is, you can't separate these two effects just by looking at the redshift. If you see a galaxy with redshift z equals 0.02, is it far away and not moving much? Or is it closer, but moving toward or away from us rapidly? You can't tell from the redshift alone. To measure peculiar velocities, you need to know the galaxy's true distance independent of its redshift. Then you can calculate what the redshift should be based on distance alone, using Hubble's law. And any difference between this expected redshift and the observed redshift must be due to peculiar velocity. But measuring distances to galaxies is hard, really hard. The Seven Samurai use several techniques, each with its own challenges. The Tully-Fisher relation, discovered in 1977 by astronomers Brent Tully and Richard Fisher. This is an empirical relationship between a spiral galaxy's rotation speed and its intrinsic luminosity. The faster a galaxy spins, the more massive it is, and the brighter it shines. Here's how you use it. First, you measure the galaxy's rotation speed by looking at its spectrum. Stars on one side of the galaxy are moving toward us, their light is blue shifted. Stars on the other side are moving away, redshifted. The broader the line, the faster the rotation. From this rotation speed, you calculate the galaxy's actual luminosity using the Tully-Fisher relation. Then you compare this calculated actual luminosity to the observed brightness. The difference tells you the distance. A galaxy that appears 100 times dimmer than expected must be 10 times farther away, because brightness decreases with the square of distance. Simple in principle, but in practice, you need to correct for the galaxy's inclination. Are we seeing it edge on or face on? For dust extinction, is some light being absorbed? For the specific wavelength you're observing, the relation is different in optical versus infrared light. Each correction introduces uncertainty. The typical uncertainty, a single Tully-Fisher distance measurement might be 20 to 30%. The fundamental plane. This is a similar technique for elliptical galaxies, which don't rotate in the simple way spirals do. The fundamental plane is a relationship between three properties: size, surface brightness, and velocity dispersion, the random motions of stars within the galaxy. By measuring two of these properties, you can calculate the third. Then, comparing the calculated size to the observed angular size gives you the distance. Again, uncertainties of 20 to 30% are typical. Surface brightness fluctuations. This clever technique exploits the fact that in a nearby galaxy, you can see the granularity caused by individual bright stars. The galaxy's surface isn't smooth, but slightly mottled. In a more distant galaxy, many more stars are blended together in each pixel of your image, so the surface appears smoother. By measuring the statistical properties of these fluctuations, you can estimate distance. Nearby galaxies are lumpier, distant galaxies are smoother. This technique works well for nearby galaxies, but requires very high-quality images. The 7 samurai spent years making these measurements. They observed hundreds of galaxies, measured distances using multiple techniques, combined the results statistically to reduce uncertainties. It was painstaking work, but gradually, a pattern emerged. As data accumulated through the late 1970s and early 1980s, the 7 Samurai team saw something remarkable in their velocity measurements. Galaxies weren't moving randomly. There was a clear, systematic pattern. Galaxies in one particular region of the sky toward the constellations Centaurus, Norma, and Triangulum Australe in the southern hemisphere were approaching us faster than expected. Based on cosmic expansion alone, the closer galaxies had small approach velocities. More distant galaxies had larger approach velocities. It was as if galaxies were falling toward us, or more accurately, they were both falling toward something in that direction. Galaxies on the opposite side of the sky showed the opposite pattern. They were receding faster than cosmic expansion alone would predict, as if being carried away from something. The interpretation was inescapable. Our local group of galaxies was moving at about 600 kilometers per second toward this region. Not just the Milky Way, the entire local group, including the Andromeda Galaxy M31, Triangulum Galaxy M33, and dozens of smaller dwarf galaxies. Moreover, it wasn't just the local group. Other nearby galaxy groups showed similar patterns. The Virgo cluster, 65 million light-years away and containing over 1,300 galaxies, was also moving in roughly the same direction. More distant structures, as far as measurements could reach out to 200 to 300 million light-years, showed consistent flows. This was big. Really big. Something out there, something massive beyond comprehension, was pulling a substantial portion of the nearby universe toward it. The gravitational influence extended across hundreds of millions of light-years, affecting the motions of millions of galaxies. But what was it? And where, exactly, was it located? The direction was clear. Roughly right ascension 13 hours 20 meters, declination -44. The distance was harder to pin down. The velocity patterns suggested somewhere between 150 and 250 million light-years away. So astronomers pointed their telescopes in that direction, expecting to see an enormous cluster of galaxies, or perhaps a supercluster, something massive enough to explain this gravitational pull. What they found was nothing they could see clearly. The coordinates of the Great Attractor 13 hours 20 meters 44 place it almost exactly behind the plane of the Milky Way galaxy. This is a problem, a big problem. You see, when you look toward the galactic plane, the disk of the Milky Way, you're looking through the densest parts of our galaxy. You're looking through hundreds or even thousands of light-years, dust and gas. And this material absorbs visible light. Interstellar dust isn't like household dust. It's made of tiny grains, typically 0.1 to 1 micrometer across, composed of silicates similar to sand, carbon including graphite, and complex organic molecules, and water ice. These grains are created in the atmospheres of dying stars and in supernova explosions, then dispersed throughout the galaxy by stellar winds and supernova shockwaves. The problem with these grains is their size. They're roughly the same size as the wavelength of visible light, 0.4 to 0.7 micrometers. When light of similar wavelength encounters a particle of similar size, it interacts strongly, either scattering in random directions or being absorbed and re-emitted as infrared heat. Look through enough dust, and visible light is almost completely blocked. Objects behind the dust are rendered invisible, no matter how bright they actually are. Astronomers call the region obscured by the Milky Way's disk the zone of avoidance. It's not a location in space, it's a direction from Earth that we can't observe clearly. Invisible light. The zone of avoidance extends roughly 10 to 20 degrees above and below the galactic plane, forming a band that wraps around the entire sky. And by cruel cosmic irony, the Great Attractor, the single most important gravitational structure affecting our motion through the universe, is located almost exactly in the middle of the densest part of the zone of avoidance. It's as if the universe has a sense of humor. You want to understand what's pulling you. Too bad I placed it in the one direction you can't easily observe. Imagine you're in a dense fog, trying to understand where a loud noise is coming from. You can hear it, You can feel vibrations through the ground. You can measure how the sound changes with time. But you can't see the source because the fog is too thick. That's the situation astronomers found themselves in regarding the Great Attractor. They knew it was there. They could measure its gravitational effects with high precision. They could calculate its approximate distance 150 to 250 million light-years, based on how velocity patterns changed with distance. They could estimate its mass tens of thousands of galaxy masses, at least based on the strength of the gravitational pull, but they couldn't see what it actually looked like. Was it a single massive cluster, multiple clusters, a diffuse distribution of dark matter? They had no way to know. Throughout the 1980s, this situation was incredibly frustrating for astronomers. Some questioned whether the Great Attractor even existed. Maybe the velocity measurements were wrong. Maybe there were systematic errors in the distance determinations. Maybe the peculiar velocity patterns could be explained by other means. Perhaps a large void on the opposite side pushing us rather than something ahead pulling us. The debate was heated and sometimes personal. Scientific careers were invested in different interpretations. Papers were published arguing for and against the Great Attractor's existence. Conferences featured vigorous discussions that sometimes bordered on arguments. But as more data came in from independent teams using different techniques, the evidence strengthened. By the mid-1980s, most astronomers accepted that our local group was indeed flowing toward a massive structure hidden behind the galactic plane. The motion was real. The Great Attractor, whatever its nature, existed. The debate shifted from does it exist to what is it, and how can we see through the dust? The answer to that second question required new technologies and new wavelengths of light. Before we move on to how astronomers finally saw the Great Attractor, I want to spend some time on the alternative explanations that were proposed. Because this is how science actually works, not as a smooth progression from ignorance to knowledge, but as a messy, contentious process where multiple ideas compete and evidence gradually favors one over others. Alternative 1. Systematic errors in distance measurements. Some skeptics argue that the peculiar velocity measurements were simply wrong. After all, measuring distances to galaxies is difficult and subject to many sources of error. The Tully-Fisher relation, for example, has scattered. Not all galaxies of a given rotation speed have exactly the same luminosity. There's variation, maybe 20 to 30% in either direction. And the relation might change with galaxy properties. Dwarf galaxies don't quite follow the same relation as giant galaxies. Gas-rich galaxies might behave differently than gas-poor galaxies. Moreover, there were concerns about Malmquist bias, a statistical effect where you're more likely to observe galaxies that are intrinsically brighter than average because they're visible to greater distances, which biases your distance estimates. If these systematic errors were correlated, if they all bias distances in the same direction. For galaxies in a particular part of the sky, they could create the illusion of a large-scale flow when none existed. Proponents of the Great Attractor argued against this by showing that multiple independent distance measurement techniques, Tully-Fisher, fundamental plane, surface brightness fluctuations, Type Ia supernovae, all showed consistent results. If the effect were just systematic errors, different techniques shouldn't agree. Alternative 2. To dipole, repel or push rather than pull. Another alternative proposed that maybe we weren't being pulled toward the Great Attractor, maybe we were being pushed away from something behind us. The idea is simple. Gravitational repulsion isn't really repulsion, it's the absence of attraction. If there's a large underdense region of void behind us, we feel less gravitational pull from that direction. This creates a net force toward the denser regions, effectively pushing us away from the void. Mathematically, you can describe our motion either as being pulled by overdense regions ahead or pushed by underdense regions behind. The two descriptions can be equivalent. Interestingly, this alternative turned out to be partially correct. In 2017, astronomers discovered what they called the dipole repeller, a large void on the opposite side of the sky from the Great Attractor. About 30% of our motion is indeed due to this void pushing us, but 70% is still the Great Attractor pulling. Both effects contribute. Alternative 3. Modified cosmology. Some theorists propose that maybe our cosmological models were wrong. Perhaps the universe's expansion doesn't work quite the way we think it does. Perhaps there are large-scale rotations or bulk flows that we haven't accounted for. If the entire nearby universe out to several 100 million light-years were rotating, or if there were some other large-scale motion, it might create velocity patterns that we're misinterpreting as flows toward a single attractor. This alternative was hard harder to rule out completely, but it faced challenges. Any modification to cosmology had to explain not just the Great Attractor flows, but all other observations, the cosmic microwave background properties, to distribution of galaxies, the observed expansion rate, etc. Most proposed modifications either conflicted with other observations or required fine-tuning of parameters. Alternative 4. There is no Great Attractor, just multiple structures. Another proposal suggested that there wasn't a single Great Attractor, but rather multiple massive structures, whose gravitational effects combined to create the observed velocity patterns. This alternative was actually closest to the truth. As we'll see, the Great Attractor region does contain multiple massive clusters, but the key insight is that these clusters are themselves part of a larger structure, a supercluster, that acts as a unified gravitational basin. So it's both true that there are multiple clusters, and true that they collectively form a single attractor. The scientific process worked as it should. Skeptics proposed alternatives, tested them against data, and gradually some were ruled out, while others were refined or incorporated into better models. The end result was a more nuanced understanding than the original simple massive cluster pulling us idea. But to move beyond debates and models, astronomers needed direct observations. They needed to see through the zone of avoidance, and that required a revolution in observational astronomy. Before we move on to how astronomers finally mapped the Great Attractor, let's talk about the name itself. The term Great Attractor was coined by the Seven Samurai team: Donald Lyndon Bell, Sandor Faber, David Burstein, Roger Davies, Alan Dressler, Robert Turlevich, and Gary Wegner in a landmark paper published in the Astrophysical Journal in 1988. The paper, titled Spectroscopy and Photometry of Elliptical Galaxies, a large-scale streaming motion in the local universe, presented their analysis of 400 elliptical galaxy observations. It was the culmination of over a decade of work. In the paper, they needed a term to describe the massive structure toward which galaxies were flowing. They chose Great Attractor for several reasons. Great because this wasn't just any concentration of mass, it was one of the largest structures in the nearby universe, affecting motions across hundreds of millions of light-years. Attractor because it was drawing in galaxies from all directions, like a gravitational whirlpool or maelstrom. The mathematics of dynamical systems uses the term attractor to describe a state toward which a system naturally evolves, and this was the cosmic equivalent. The name has a certain ominous quality, which is appropriate. There's something unsettling about learning your galaxy is being pulled by invisible forces toward an unseen destination. It sounds like science fiction, but it's established science. Names are powerful in science. They shape how we think about phenomena. Before having a name, the Great Attractor was just that structure behind the galactic plane causing peculiar velocities. After being named, it became a real object in astronomers' minds, something to study, map, understand. The name Great Attractor also captured the public imagination in a way that technical terms, like massive overdensity in the enormous Antares region, never could. It appeared in popular science articles, books, documentaries. It helped bring cutting-edge cosmology to broader audiences. Of course, as we'll see, the name is somewhat misleading. The Great Attractor isn't a single object, but the gravitational center of a vast supercluster. And it's not even the largest attractor in the nearby universe. That distinction goes to the Shapley Supercluster, which is pulling the Great Attractor itself. But in 1988, astronomers didn't know this yet. The Great Attractor was a mystery, a massive unseen force pulling the local universe. And solving that mystery would require looking at the universe in entirely new ways. Which brings us to the revolution in infrared and radio astronomy have finally revealed what the Great Attractor actually looks like. End of Part 1. Continued in next file. Act 3. Seeing Through the Fog, Chapter 3.1. Why infrared light changes everything. To understand how astronomers finally saw the Great Attractor, we need to understand a fundamental principle of physics. Different wavelengths of light interact differently with matter. Let me give you an everyday example. On a foggy morning, you can barely see buildings across the street. Invisible light, the fog scatters the light in all directions. But if you could see in radio waves, which have much longer wavelengths, you'd see right through the fog as if it weren't there. This is why radar works. Radio waves penetrate fog, clouds, even light rain. The same principle applies to cosmic dust. Interstellar dust grains are typically 0.1 to 1 micrometer across. This happens to be almost exactly the size of visible light wavelengths. Blue light is 0.4 micrometers, red light, is 0.7 micrometers. When light of similar wavelength encounters a particle of similar size, strong interaction occurs. The light scatters in random directions, some forward, some backward, some to the sides. After passing through enough dust, the original beam is completely dispersed. This is called Rayleigh scattering when particles are smaller than the wavelength, and Mie scattering when they're comparable. The result is the same. Light doesn't get through. But here's the key. The amount of scattering depends on wavelength. Shorter wavelengths blue light scatter much more than longer wavelengths red light. This is why sunsets are red-blue light scatters out of the beam, as sunlight passes through the atmosphere, leaving red light to reach your eyes. Infrared light has even longer wavelengths than visible red light, typically 1 to 100 micrometers. For these longer waves, dust grains are smaller obstacles. The amount of scattering decreases dramatically as wavelength increases. The mathematical relationship is that extinction, the technical term for light being blocked, decrease is roughly proportional to 1 over wavelength. So light at 2 micrometers near-infrared experiences about 3.5 times less extinction than light at 0.7 micrometers red visible light. Light at 10 micrometers mid-infrared experiences about 14 times less extinction. This means you can see through dust in infrared that completely blocks visible light. But there's a catch. Very few astronomical objects emit much infrared light naturally. Stars are hot thousands of Kelvin, so they emit mostly visible and ultraviolet light. Non-infrared. To observe galaxies in the infrared, you're mostly seeing the light from their stars that's been absorbed by dust and re-emitted as infrared heat. This works, but it's much dimmer than the original starlight. Still, even seeing galaxies dimly in infrared is better than not seeing them at all in visible light. The first major infrared survey that could penetrate the zone of avoidance was launched in 1983. The Infrared Astronomical Satellite, or IRAs. Chapter 3.2. IRAs. The pioneer that mapped hidden galaxies. The Infrared Astronomical Satellite IRAs was a joint project of the United States NASA, the Netherlands NIVER, and the United Kingdom CIRC. It was launched on January 25, 1983, aboard a Delta rocket from Vandenberg Air Force Base in California. IRAs was remarkable for its time. It carried a 60-centimeter telescope cooled to just a Kelvin, 2 degrees above absolute zero, by liquid helium. Why so cold? Because the telescope itself emits infrared radiation if it's warm, which would overwhelm a faint infrared light from distant galaxies. By cooling it to nearly absolute zero, its own emission becomes negligible. The satellite observed at 4 infrared wavelengths, 12, 25, 60, and 100 micrometers. These wavelengths were chosen to be sensitive to dust at different temperatures. Cold dust 20 to 40 Kelvin, like that in the outer regions of galaxies, emits mainly at longer wavelengths 60 to 100 micrometers. Warmer dust 40 to 100 Kelvin, like that in star-forming regions, emits at shorter wavelengths 12 to 25 micrometers. IRAs surveyed the entire sky over 10 months, from January to November 1983. Before its helium coolant ran out, it detected about 350,000 infrared sources, including roughly 75,000 galaxies. Many of these galaxies had never been seen before. They were hidden behind the zone of avoidance in visible light but revealed in infrared. For the Great Attractor specifically, IRAs revealed something stunning. The region toward which we were being pulled wasn't empty at all. It contained hundreds of galaxies, including several massive clusters. The most prominent structure was the Norma cluster, at a distance of about 220 million light-years. This massive cluster contains hundreds of individual galaxies concentrated in a region, about 10 million light-years across. The total mass is equivalent to thousands of Milky Ways. IRAs also revealed the Centaurus cluster at 170 million light-years, and numerous smaller groups and clusters throughout the region. But IRAs had limitations. It could detect galaxies, but couldn't measure their distances or velocities directly. It provided positions and brightnesses, but not the three-dimensional structure needed to fully map the Great Attractor. That would require follow-up observations, spectroscopy to measure redshifts, and systematic surveys to map the region completely. Still, IRAs transformed the situation. The zone of avoidance was no longer a complete blank spot. Astronomers now knew where to look for the structures causing our motion. The fog was lifting. Chapter 3.3. To mass and the detailed mapping. The next major step came with the 2-micron all-sky survey, or 2 mass, conducted from 1997 to 2001. Unlike IRAs, which observed in mid to far infrared, TMAS observed in the near-infrared, wavelengths of 1.25, 1.65, and 2.17 micrometers, designated as J, H, and K bands in astronomical notation. These wavelengths are just beyond what human eyes can see. If our eyes were slightly more sensitive, we could see this light. Near-infrared has advantages and disadvantages compared to mid-infrared. The disadvantage is that it doesn't penetrate dust quite as well. At 2 micrometers, you still experience about 30% of the extinction you'd get in visible red light at 0.7 micrometers. That's much better than visible light, but not as good as the 10 to 100 micrometer wavelengths IRAs used. The advantage is that you're seeing actual starlight, just the end of star spectrum, not dust emission. This makes galaxies appear brighter and easier to detect. You can see more detail in galaxy structure, and you can identify different types of galaxies based on their near-infrared colors. TMAS used two automated 1.3-meter telescopes, one at Mount Hopkins in Arizona and one at Cerro Tololo in Chile, giving complete coverage of northern and southern skies. The survey ran for 4 years and detected over 1.5 million galaxies. For the Great Attractor region, TMAS provided unprecedented detail. It revealed not just the major clusters, but also the filamentary structure connecting them, the cosmic web of galaxies, linking the Norma cluster, Centaurus cluster, and other structures, combined with redshift measurements measuring each galaxy's spectrum to determine its distance and velocity. Astronomers could now create three-dimensional maps of the Great Attractor region. What they found was more complex than a single massive cluster. The region contained multiple clusters and superclusters arranged in a complex network. The Norma cluster was the largest concentration, but it was surrounded by other structures, all contributing to the gravitational pull. But even the Norma cluster, as massive as it is, couldn't fully explain the observed velocities. The numbers didn't quite add up. There must be more mass either in smaller clusters not yet detected or in diffuse dark matter halos surrounding visible structures. This brings us to one of the great mysteries of modern astronomy, dark matter. Chapter 3.4. Radio observations and neutral hydrogen. While infrared observations revealed the distribution of stars and dust, radio observations provided a completely different view: the distribution of gas. The key to radio observations of galaxies is the 21-centimeter line of neutral hydrogen. Here's how it works. Hydrogen, the most abundant element in the universe, can exist in neutral form, 1 proton and 1 electron, or ionized form, just the proton. In galaxies' outer regions and in the intergalactic medium, most hydrogen is neutral. The electron in a hydrogen atom has a property called spin, which can be either parallel or antiparallel to the proton spin. The parallel configuration has slightly more energy, very rarely about once every 10 million years per atom. The electron flips from parallel to antiparallel, releasing a tiny amount of energy as a radio photon with a wavelength of 21.106 centimeters, frequency 1420.4 millihertz. This transition is incredibly unlikely for any individual atom, but galaxies contain so many hydrogen atoms, typically 109 to 1011 solar masses worth, that collectively they emit detectable 21 cm radiation. Moreover, the Doppler shift of this line tells you the gas velocity. If a galaxy is rotating, one side's hydrogen is approaching you blue-shifted to slightly shorter wavelengths, while the other side recedes red-shifted to slightly longer wavelengths. You can map the rotation curve and total mass. Most importantly, for the Great Attractor, radio waves penetrate dust perfectly. The zone of avoidance is completely transparent at radio wavelengths. 21 cm observations could detect galaxies and measure their redshifts right through the galactic plane. The Parkes Radio Telescope in Australia, with its 64-meter dish, conducted several surveys of the zone of avoidance through the 1990s and 2000s. These surveys detected thousands of galaxies, measured their redshifts, and mapped the three-dimensional structure. Combined with optical and infrared observations were available, astronomers built increasingly complete maps of the Great Attractor region. The picture that emerged was complex and fascinating. The Great Attractor wasn't a single object, but a region of space, containing multiple massive clusters surrounded by diffuse structures, all connected by filaments of galaxies, part of the cosmic web on the largest scales. But there was still something missing from this picture, something fundamental. Divisible galaxies, stars, gas, dust accounted for perhaps 15% of the total mass needed to explain the gravitational pull. Where was the other 85%? The answer: dark matter. Chapter 3.5. The complete picture emerges by the early 2000s, combining infrared, radio, and optical observations. Astronomers had mapped the Great Attractor region in detail. Here's what they found. The Norma Cluster Echo 3627, the largest single structure, located about 220 million light-years away. This massive cluster contains hundreds of galaxies concentrated in a region, roughly 10 million light-years across. The dominant galaxies are mostly giant ellipticals, old-ray, massive galaxies formed through mergers. The cluster is gravitationally mature, having pulled in galaxies from a vast surrounding region. The Centaurus Cluster Echo 3526, slightly closer, about 170 million light-years. This is another major cluster containing several hundred galaxies. It's slightly less massive than Norma, but still a significant gravitational anchor. The Shapley Supercluster, an extended structure of galaxies, stretching across 100 million light-years, connecting multiple smaller clusters and groups. Numerous galaxy groups throughout the region. Dozens of smaller groups, each containing 10 to 100 galaxies, fill the space between major clusters. Filamentary structures, chains of galaxies connecting the clusters, part of the cosmic web we'll discuss in more detail later. The total visible mass in stars and gas, approximately 10,000 to 20,000 times the Milky Way's mass. That sounds enormous, and it is. The calculations based on the observed gravitational effects, the velocities of galaxies being pulled toward the region, suggested the total mass was 50,000 to 100,000 Milky Way masses. Where was the extra mass? There were no hidden clusters large enough to account for it. The only explanation: dark matter. The Great Attractor is dominated by dark matter. Just like every other large-scale structure in the universe, the galaxies we see are like lights floating on an invisible ocean. The dark matter provides the gravitational scaffolding, and visible matter merely traces its distribution. But what is dark matter, and how do we know it exists if we can't see it? That's what we're going to explore next. Act 4. The Dark Matter Skeleton. Chapter 4.1. The Invisible Universe. Here's something that might shock you. Everything we've talked about so far, the galaxies, the clusters, the Norma Cluster, the Great Attractor, even all the stars in the observable universe, represents only about 5% of the universe's total mass energy. Another 27% is dark matter that doesn't emit, absorb, or reflect light of any wavelength. It's completely invisible to all electromagnetic radiation. It only interacts through gravity. And 68% is dark energy, something even more mysterious that we'll discuss later in relation to the universe's future. But let's focus on dark matter for now, because it's absolutely central to understanding the Great Attractor and all cosmic structure. Dark matter doesn't emit light, doesn't absorb light passing through it, doesn't reflect light. As far as we can tell, it doesn't interact electromagnetically at all. It might not even interact through the strong or weak nuclear forces. Though some theoretical models suggest weak interactions, the only way we know it exists is through gravity. And gravity provides overwhelming evidence. For every kilogram of normal matter, atoms, molecules, protons, neutrons, electrons, everything we can see and touch, there are roughly 5.4 kilograms of dark matter. In the universe as a whole, dark matter outweighs normal matter by more than 5 to 1. In galaxy clusters, like those in the Great Attractor region, the ratio is even more extreme. For every kilogram of stars, there are 2 to 3 kilograms of hot gas between the galaxies, and 30 to 50 kilograms of dark matter surrounding the whole structure. The Great Attractor is primarily a dark matter structure. The galaxies we see are like floating lights marking the location of a vast, invisible gravitational potential well. The dark matter provides the gravitational pull that's dragging us and millions of other galaxies forward. But I realize I'm asking you to accept something extraordinary, that most of the universe is made of stuff we've never detected directly, never seen, never touched. Invisible matter that we only infer from its gravitational effects. So let me give you the evidence, because it's overwhelming, and it comes from multiple independent sources. Any one line of evidence might be explained away, but taken together, they paint an undeniable picture. Chapter 4.2. Evidence 1. Galaxy rotation curves. The first major evidence for dark matter came from studying how galaxies rotate. In the 1970s, astronomer Vera Rubin and her collaborators at the Carnegie Institution measured the rotation speeds of stars in spiral galaxies at different distances from the galactic center. This is relatively straightforward. You observe the galaxy's spectrum at different positions. Stars on one side are moving toward you blue-shifted. Stars on the other side are moving away red-shifted. The amount of shift tells you the rotation speed. Based on visible matter alone, stars, gas, dust, you can calculate how fast stars should orbit at each distance. The physics is the same as planets orbiting the sun. Orbital velocity depends on the enclosed mass and distance. Farther from the center, there's less mass inside the orbit, so stars should orbit more slowly. In our solar system, this works perfectly. Mercury orbits at 47 kilometers per second, Earth at 30 kilometers per second, Mars at 24 kilometers per second, Jupiter at 13 kilometers per second, Neptune at just 5 kilometers per second. Orbital speed decreases with distance exactly as Newton's laws predict. But galaxies don't work that way. Rubin found that stars far from galactic centers at the outer edges, where very few stars are visible, orbit just as fast as stars closer in. Instead of declining, rotation curves are flat. A star 50,000 light-years from the center orbits at roughly the same speed as 125,000 light-years from the center. This only makes sense if there's additional invisible mass providing gravitational pull, and not just a little extra mass a lot. Typically, the dark matter halo must contain 5 to 10 times as much mass as all the visible stars. Moreover, the dark matter must be distributed differently than visible matter. Visible matter stars concentrates toward the galactic center. Dark matter must extend much farther out, forming a roughly spherical halo surrounding the visible disk. This was revolutionary. It suggested that galaxies aren't primarily made of stars, they're primarily made of something we can't see. The stars are just the visible tip of a much larger, invisible structure. Initial skepticism was intense. Maybe Rubin had made an error. Maybe the gas wasn't where she thought it was. Maybe the gravity laws needed modification. But as more galaxies were studied, hundreds, then thousands, the pattern held. Every spiral galaxy showed flat rotation curves extending as far as measurements could reach. Every single one required dark matter to explain the observations. And it wasn't just spiral galaxies. Elliptical galaxies showed similar evidence from the velocities of their stars and globular clusters. Dwarf galaxies, some containing more dark matter than visible matter, showed the same pattern. The evidence was undeniable. Galaxies contain vast amounts of invisible matter. Chapter 4.3. Evidence 2. Gravitational lensing. The second major line of evidence comes from gravitational lensing, the bending of light by massive objects. Einstein's general relativity predicts that mass curves spacetime, and light follows these curves. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, its path bends. This is called gravitational lensing. The amount of bending depends on the mass of the lensing object. More mass means stronger gravitational field means more bending. By measuring the bending, you can calculate the mass even if you can't see that mass directly. Galaxy clusters create strong gravitational lenses. Background galaxies appear distorted, stretched into arcs and multiple images. The shapes and positions of these distorted images allow detailed mapping of the cluster's mass distribution. When astronomers map cluster masses this way, they find the same result. Clusters contain 5 to 10 times more mass than visible in stars and gas. The extra mass is dark matter. What's particularly compelling about lensing is that it's a completely independent technique from rotation curves. It doesn't rely on understanding galaxy dynamics or gas physics. It's pure geometry. Light follows curved paths through curved spacetime, and the degree of curvature tells you the mass. Moreover, lensing allows mapping the dark matter distribution in detail. In the early 2000s, astronomers created the first dark matter maps using weak lensing, subtle distortions of many background galaxies that, analyzed statistically, reveal foreground mass concentrations. These maps showed dark matter range in a cosmic web of filaments connecting nodes, where galaxy clusters sit. The Great Attractor region, when mapped with gravitational lensing, shows exactly this structure. Multiple nodes of dark matter concentration connected by filaments, with the Norma cluster sitting in the largest, deepest potential well. One famous example is the Bulla cluster, observed in detail in 2006. This is a system of two galaxy clusters that have collided. During the collision, the gas in both clusters, which is normal matter, interacted, collided, and stayed behind at the collision site, glowing brightly in X-rays. But the dark matter, which doesn't interact except through gravity, passed right through itself. Gravitational lensing maps showed that most of the mass passed through the collision and is now on the far sides of the system, completely separated from most of the visible gas. This is perhaps the most direct evidence for dark matter. The mass measured by lensing is in a different location than the normal matter measured by X-ray emission. The only explanation is that most mass is in some invisible form, dark matter, that interacts differently than normal matter. Chapter 4.4. Evidence 3. Cosmic microwave background. The third major line of evidence comes from the cosmic microwave background, the oldest light in the universe. The CMB was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Before this moment, free electrons scattered photons constantly, making the universe opaque like fog. After recombination, photons could travel freely, and the universe became transparent. The CMB carries information about conditions in the early universe, encoded in tiny temperature variations about 1 part in 100,000. These variations reflect density differences in the primordial gas. Slightly denser regions were slightly hotter compressed. Slightly less dense regions were slightly cooler. Here's the key. The pattern of these temperature variations depends on the universe's composition. How much normal matter, how much dark matter, how much dark energy. Normal matter, baryonic matter, interacts with photons. In the early universe, baryons and photons were tightly coupled through frequent interactions. Gravity pulled baryonic matter into overdense regions, but photon pressure pushed it back out. The result was oscillations, acoustic waves, in the primordial plasma. Dark matter, not interacting with photons, didn't oscillate. It just accumulated in overdense regions through gravitational collapse, unaffected by radiation pressure. This difference creates a characteristic signature in the CMB temperature pattern. The angular scale of temperature variations, the relative amplitudes of different scales, the detailed shape of the power spectrum, all these depend on the relative amounts of baryonic matter and dark matter. When satellites like WMAP 2001 to 2010 and Planck 2009 to 2013 measured the CMB in exquisite detail, they determined the universe's composition with percent-level precision. About 5% normal baryonic matter, about 27% dark matter, about 68% dark energy. These values are determined independently of galaxy rotation curves and gravitational lensing, yet they agree perfectly. 3 completely different techniques converge on the same answer. The universe is dominated by dark matter and dark energy. For the Great Attractor specifically, this matters because it tells us the structure is fundamentally a dark matter structure. The 15% visible mass we can see is just the traceable component of a much larger dark matter concentration. Chapter 4.5. Evidence 4. Large-scale structure formation. The fourth major evidence comes from computer simulations of how structure forms in the universe. Starting from initial conditions matching the CMB observations, tiny density variations at 380 years after the Big Bang, physicists simulate how structure grows over billions of years. As gravity amplifies these initial variations, these simulations involve billions of particles interacting through gravity, run on supercomputers for weeks or months of processing time. Different simulations try different assumptions: only normal matter, only dark matter, various ratios, etc. The results are clear. Simulations with only normal matter don't produce the observed large-scale structure. Galaxies form too late. Clusters are too small. The cosmic web doesn't look right. But simulations including dark matter, with the proportions measured from the CMB, reproduce the observed universe remarkably well. The distribution of galaxies, the sizes and masses of clusters, the hierarchical structure from galaxies to clusters to superclusters, it all matches observations. These simulations show how the Great Attractor and structures like it formed. Initial overdensities in the dark matter distribution, seeded by quantum fluctuations during inflation, gravitationally attract more dark matter and normal matter. Over billions of years, these overdensities grow into the nodes and filaments we see today. The simulations predict structures exactly like the Great Attractor, massive nodes in the cosmic web, where multiple filaments converge, containing tens of thousands of galaxies arranged in clusters and groups. Chapter 4.6. What is dark matter? So the evidence is overwhelming. Dark matter exists. It dominates the universe's mass. It provides the gravitational scaffolding for all cosmic structure. What is it actually made of? This is one of the most embarrassing admissions in modern physics. We have no idea. We know what it's not. Not normal atoms, baryons, and forms we can't see easily. Dead stars, planets, gas. The CMB observations constrain the total amount of baryonic matter to 5% of the universe. And we've accounted for most of that in stars and gas. Not neutrinos, we can detect those. And they're to light and move too fast to form structures, like galaxies. Not black holes from dead stars. Gravitational lensing surveys would have detected them. So it must be something else. Some particle or particles that interact through gravity, but not electromagnetically, and possibly not through strong or weak nuclear forces either. Deleting candidates. WIMPs, weakly interacting massive particles. Hypothetical particles with masses 10 to 1,000 times a proton, interacting only through gravity and possibly the weak nuclear force. Many extensions of the standard model of particle physics predict such particles. They'd be produced in the early universe and persist today as a sea of invisible particles, filling the universe. Dozens of experiments have searched for WIMPs, giant detectors deep underground looking for rare collisions between WIMPs and normal matter. As so far, nothing. The parameter space is shrinking. If WIMPs exist, they're more weakly interacting than expected. Axions, extremely light particles 10 to 5 times an electron's mass or less, originally proposed to solve a different problem in particle physics. They'd be produced in enormous numbers in the early universe. Recent experiments using strong magnetic fields and sensitive detectors are searching for axion signatures. Sterile neutrinos, a hypothetical fourth type of neutrino that doesn't interact through the weak force making it sterile. These would be heavier than regular neutrinos and could account for dark matter. Primordial black holes. Black holes formed in the first second after the Big Bang from density fluctuations. If these black holes had specific mass ranges around 10 to 8 to 10 to 5 solar masses, or around 10 to 100 solar masses, they might avoid detection constraints and account for dark matter. This is gaining renewed interest after LIGO detected black hole mergers. Modified gravity. Some theorists suggest dark matter doesn't exist at all. Instead, our law of gravity, general relativity, needs modification on large scales. Various theories, like modified Newtonian dynamics or emergent gravity, try to explain observations without dark matter. Most struggle to explain all observations simultaneously, particularly the CMB and gravitational lensing. The truth is, we're stuck. We know dark matter exists with near certainty. We can map where it is, but we don't know what it is. This is actually exciting from a scientific perspective. It means there's fundamental physics we haven't discovered yet. New particles, new forces, new principles. When we figure out what dark matter is, it will likely revolutionize physics as much as quantum mechanics did in the early 20th century. For the Great Attractor, though, the dark matter mystery doesn't prevent us from studying it. We can map the dark matter distribution using gravitational lensing. We can calculate its mass from dynamical effects. We can understand how it shapes the motion of galaxies. We just can't hold it in our hands or detect it directly yet. End of Part 2. Continued in next file. Act 5. Laniakea. The supercluster we call home. Chapter 5.1. Cosmic Flows, a revolutionary approach. In 2014, a team led by astronomer Brent Tully at the University of Hawaii published a paper in the journal Nature that fundamentally redefined our place in the universe. The paper was titled The Laniakea Supercluster of Galaxies, and it revealed that the Great Attractor isn't a separate structure. It's the gravitational center of an enormous supercluster that we've been part of all along. But to understand this discovery, we need to understand the revolutionary technique Tully's team used: mapping cosmic flows. Traditional approaches to defining large-scale structures focused on galaxy positions. If you saw a concentration of galaxies in a region of space, you called it a cluster or supercluster. Simple enough. But this approach has a fundamental problem. It doesn't account for dynamics. Galaxies might be near each other in space but moving in different directions, not gravitationally bound together. Tully's insight was different. Instead of mapping where galaxies are, map where they're going. Trace their flows through space like mapping rivers on Earth. Here's the concept. Galaxies aren't just moving outward due to cosmic expansion. They also have peculiar velocities, real motions through space caused by gravitational attraction toward overdense regions and repulsion from underdense regions voice. These peculiar velocities trace the gravitational field. Where flows converge, there must be a mass concentration pulling things together. Where flows diverge, there must be a void or boundary between different basins of attraction. It's exactly like watersheds on Earth. Water flows downhill from high elevations toward low points, rivers, lakes, oceans. If you map which direction water flows at every point, you can define drainage basins. Everything flowing toward the Atlantic Ocean is part of the Atlantic watershed. Everything flowing toward the Pacific is part of the Pacific watershed. The boundary between them is the continental divide. Tully proposed doing the same thing for the universe. Map peculiar velocities for thousands of galaxies. Trace where they're flowing. Define cosmic watersheds, regions of space whose contents flow toward common basins. This technique is called cosmography, and it's extraordinarily difficult to do in practice. The challenge is measuring distances accurately enough to determine peculiar velocities. Remember, when you observe a galaxy's redshift, you're seeing both cosmological redshift from expansion and Doppler shift from peculiar velocity. To separate these, you need the galaxy's true distance independent of redshift. Tully's team spent years compiling distance measurements for about 8,000 galaxies within 500 million light-years. They used Tully-Fisher distances from rotation speeds, fundamental plane distances from elliptical galaxy properties, Typeus supernova distances, surface brightness fluctuation distances, every available technique. With these distance measurements, they calculated peculiar velocities, the difference between observed redshift and expected redshift based on distance and expansion rate. Then came the computational challenge, converting 8,000 velocity measurements into a smooth, three-dimensional flow field. This required sophisticated algorithms that interpolate between measurements, accounting for uncertainties and potential systematic errors. The result was a velocity field map showing how galaxies flow through our local universe, out to 500 million light-years in all directions. Chapter 5.2. The revelation of Laniakea. When Tully's team analyzed their velocity field, they discovered something remarkable. The flows weren't just converging on the Great Attractor, they were converging on a much larger structure, a gravitational basin 520 million light-years across, containing roughly 100,000 galaxies. This wasn't just a collection of galaxy clusters, it was a dynamically coherent structure, a region of space, whose contents all flow toward a common center, a true supercluster defined not by position, but by motion. The team needed a name for this structure. They chose Laniakea, from Hawaiian words meaning immeasurable heaven. The name is fitting. This is our cosmic home on the largest scales, and it is indeed immeasurably vast by human standards. Let me give you a sense of scale. The Milky Way galaxy, 100,000 light-years across the local group, 10 million light-years across the Virgo cluster, 33 million light-years across Laniakea supercluster, 520 million light-years across Laniakea, contains approximately 100,000 large galaxies, each containing hundreds of billions of stars. If you tried to count every star in Laniakea at 1 per second, it would take trillions of years, far longer than the universe has existed. The total mass is approximately 1017 solar masses. That's 100 quadrillion times the mass of our Sun. 100 million billion solar masses, 100, 0 Milky Way galaxies worth of mass, and remember, about 85% of that mass is dark matter. The visible stars and gas we can see are just a small fraction of Laniakea's total mass. The boundaries of Laniakea are defined by velocity field watershed surfaces, where flows transition from converging toward Laniakea's center to flowing toward neighboring basins. These boundaries are not sharp walls, but transition zones typically 20 to 50 million light-years thick. Within these boundaries, every galaxy is flowing toward the gravitational center. Some are flowing directly toward it. Others are taking more circuitous routes, perhaps first flowing toward intermediate attractors, like the Virgo cluster, before continuing toward the ultimate center. But all flows eventually lead to one place, the Great Attractor basin, at the heart of Laniakea, where the Norma cluster sits. Chapter 5.3. Our position in Laniakea, or are we in this vast structure? The Milky Way sits on the outskirts of Laniakea, near the boundary with the Perseus-Pisces supercluster. We're in the suburbs, as it were, not downtown. Specifically, we're located about 250 million light-years from Laniakia's center near the Virgo cluster, which sits about 65 million light-years away, flowing toward Virgo at roughly 200 to 300 kilometers per second. But Virgo itself flows toward the Great Attractor at 300 to 400 kilometers per second. So our net motion toward Laniakia's center is about 600 kilometers per second. We're falling through Laniakia's gravitational potential well, picking up speed as we go. In cosmic terms, we're like a ball rolling downhill, accelerating toward the bottom of a valley. Here's our complete cosmic address: Earth, our home planet solar system, Sun plus 8 planets, Orion arm, minor spiral arm of the Milky Way galaxy, barred spiral, 100 light-years across, local group, 80 galaxies including Milky Way and Andromeda, local sheet, flattened structure of galaxy groups, Virgo cluster region. We're falling toward this cluster, Laniakea Supercluster, our supercluster. 520 million light-years across, observable universe to 93 billion light-years across. Before 2014, we would have said Virgo supercluster instead of Laniakea Supercluster. But the Virgo supercluster was defined arbitrarily based on galaxy positions, not dynamics. It included galaxies not actually flowing together. Laniakea represents a real physical structure, a gravitationally bound region, flowing toward a common center. This is a much more meaningful definition. Interestingly, the Virgo supercluster, as previously defined, is actually parts of two separate superclusters. Most of it is part of Laniakea, but some outlying regions belong to neighboring basins. Chapter 5.4. The geography of Laniakea. Let me give you a detailed tour of our supercluster. The Great Attractor, the central basin, 220 million light-years from us, contains the Norma cluster Echo 3627, the most massive single cluster in Laniakea. Also includes the Centaurus cluster and multiple smaller groups. This is the low point in Laniakea's gravitational potential. All flows converge here. The Virgo cluster, minus 65 million light-years from us. This cluster of 1,300 galaxies was long thought to be our main gravitational anchor. It's a major waypoint on our journey. We're flowing toward Virgo, which is itself flowing toward the Great Attractor. The local group, our immediate neighborhood, dominated by Milky Way and Andromeda. Total mass about 2 trillion solar masses. In 4 billion years, Milky Way and Andromeda will merge, but the combined system will still be flowing through Laniakea. The Fornax cluster, about 65 million light-years away, similar distance to Virgo, but different direction, containing about 350 galaxies, also flowing toward the Great Attractor. The Hydra Centauri supercluster, an extended structure connecting multiple clusters between us and the Great Attractor. The Pavoindus telescopium clouds, structures in the southern celestial hemisphere, part of the extended cosmic web. The Leo spur, a filament extending from the Virgo cluster toward the Leo constellation region. These aren't separate entities, they're all connected parts of a single flowing structure, like rivers and tributaries flowing toward an ocean. Galaxies and galaxy groups flow toward the central basin. The structure isn't uniform. Some regions are dense with galaxies, others relatively empty, though still denser than cosmic voice. Filaments of galaxies connect the major clusters. These filaments are part of the larger cosmic web we'll discuss shortly. Chapter 5.5. Neighbors and boundaries. Laniakea doesn't exist in isolation. It has neighbors, other superclusters with their own basins of attraction. Perseus Pisces supercluster, on one side of Laniakea, about 250 million light-years from center to center. A comparably massive structure. The boundary between Laniakea and Perseus Pisces is a watershed surface where flows transition from one basin to the other. Some galaxies near this boundary show complex motions, first flowing one way, then another, as competing gravitational poles vie for dominance. Shapley Supercluster, beyond the Great Attractor, about 650 million light-years away, lies an even more massive structure. The Shapley Supercluster is the largest concentration of galaxies within 1 billion light-years. It contains more than 10,000 galaxies in at least 25 major clusters. Total mass, roughly 10 times Laniakea's mass. And here's the kicker. Shapley is pulling too. Recent studies suggest the entire Laniakea supercluster is flowing toward Shapley at perhaps 250 to 300 kilometers per second. So our motion is layered. 200 to 300 kilometers per second toward Virgo. Virgo moves 300 to 400 kilometers per second toward Great Attractor. Great Attractor moves 250 to 300 kilometers per second toward Shapley. We're caught in nested gravitational flows. Structure within structure, all the way up to the largest scales, to dipole, repeller. On the opposite side of the sky from the Great Attractor, discovered in 2017. This is a large underdense region of void containing few galaxies. It's pushing as well as Laniakea pulling. About 30% of our motion comes from this void's negative gravity. Think of it like this: you're standing on a hill, the dipole, repeller that slopes down into a valley, Laniakea basin. You're being pulled by gravity toward the valley floor, but you're also being pushed by the slope of the hill you're standing on. Both effects contribute. The cosmic web connection. Laniakea itself is part of the larger cosmic web, a universal structure of filaments, nodes, and voids extending throughout the observable universe. Laniakea is one node in this vast network, connected by filaments to other nodes. Surrounded by voids, the discovery of Laniakea changed our cosmic address and our understanding of our place in the universe. We're not just members of a galaxy, a group, a cluster. We're part of a supercluster defined by shared motion, a vast river of galaxies flowing together through the cosmic web. But this raises questions. Where are we ultimately going? Will we ever reach the Great Attractor? What's Laniakea's fate? To answer these questions, we need to talk about dark energy and the universe's expansion. Act 6. Our Cosmic Destiny, Chapter 6.1. Will we reach the Great Attractor? Let's do some math. Actually, let me do the math, you just follow along. We're moving toward the Great Attractor at 600 kilometers per second. The Great Attractor is 220 million light-years away. At our current speed, how long would it take to get there? Distance speed equals time 220 million light-years, 600 kilometers per second equals. We need to convert units. 1 light-year is 9.461012 kilometers. So 220 million light-years is 2.081021 kilometers. 2.081021 kilometers, 600 kilometers per second equals 3.471018 seconds equals 110 billion years. So at our current speed, we'd reach the Great Attractor in about 110 billion years. But wait, that calculation assumes the Great Attractor isn't moving, and that we maintain constant speed, and that space itself isn't expanding. None of these assumptions are true. Space is expanding. According to Hubble's law, distant objects recede due to cosmic expansion at a rate proportional to their distance. The current expansion rate, the Hubble constant, is about 70 kilometers per second per megaparsec. 1 megaparsec equals 3.26 million light-years. The Great Attractor at 220 million light-years away is 67.5 megaparsecs distant. Therefore, expansion alone makes it recede at 67.570 equals 4,725 kilometers per second. But we're moving toward it at 600 kilometers per second. Net motion, 4,725 minus 600 equals 4,125 kilometers per second apart. We're falling toward the Great Attractor, but the expansion of space is carrying it away from us faster than we're falling toward it. The gap is widening at 4,125 kilometers per second. We'll never reach it at current conditions, but conditions aren't constant. As we fall toward the Great Attractor, we'll speed up, gravity accelerates us, and as space expands, the expansion rate between us might change. It depends on the universe's matter and dark energy content. So the real question is, over time, does our infall velocity increase faster than expansion, or does expansion win? The answer depends on dark energy. Chapter 6.2. Dark energy and accelerating expansion. In the late 1990s, 2 independent teams of astronomers were measuring distances to very distant supernovae to determine how the universe's expansion had changed over time. They expected to find that expansion was slowing down due to gravity. Instead, they discovered that expansion is accelerating. This was so shocking that both teams checked their analysis multiple times, certain they'd made an error. They hadn't. In 2011, the leaders of both teams, Saul Perlmutter, Brian Schmidt, Adam Rees, shared the Nobel Prize in Physics for this discovery. Something is pushing space apart, overwhelming gravity's attractive pull. We call this mysterious something dark energy, though we have no idea what it actually is. Dark energy has bizarre properties. Unlike matter, which clumps and concentrates in galaxies and clusters, dark energy is smoothly distributed throughout space. It doesn't cluster. Its density doesn't decrease as space expands or decreases very slowly. As the universe expands and matter becomes more dilute, dark energy's relative importance increases. Today, dark energy accounts for about 68% of the universe's total energy density. Dark matter is 27%, normal matter is 5%. But in the early universe, matter dominated. When the universe was younger and denser, matter's gravity was strong enough to slow expansion significantly. Dark energy was always present but negligible compared to matter's gravitational effects. Sometime around 5 to 6 billion years ago, as the universe expanded and matter became more dilute, dark energy began to dominate. Expansion started accelerating. This acceleration has profound implications for large-scale structure and cosmic flows. When expansion accelerates, distant objects accelerate away from us. This means that structures not already gravitationally bound will never come together. The expansion carries them apart faster than gravity can pull them together. Galaxy clusters are gravitationally bound. Gravity is strong enough that expansion doesn't pull them apart. Superclusters, like Laniakea, are not gravitationally bound. They're held together temporarily by gravity, but expansion is already winning and will eventually tear them apart. For the Great Attractor specifically, we're flowing toward it, but expansion is carrying it away faster. And as dark energy continues to dominate, this expansion will accelerate further. The gap between us and the Great Attractor will widen ever faster. We'll never reach it. Chapter 6.3 The Future of Laniakea. Billions of years forward. Let's project forward into the deep future and trace Laniakea's fate. This is speculative. We can't predict the future with certainty, but based on our current understanding of dark energy and cosmic expansion, here's what will likely happen. 4 billion years from now, the Milky Way and Andromeda collide and merge. This is one of the few future events we can predict with confidence. The two galaxies are gravitationally bound, approaching at about 110 kilometers per second. Their collision is inevitable. The merger will take 1 to 2 billion years, producing a giant elliptical galaxy astronomers call Milky Way. But even as this dramatic local event occurs, Milky Way will still be flowing through Laniakea, will still be falling toward Virgo, which may have merged with other nearby clusters by then. Virgo will still be flowing toward the Great Attractor. 10 to 20 billion years. Most local group galaxies have merged into Milky Way. This includes Triangulum and dozens of dwarf galaxies. Some outlying dwarfs may escape. Drifting into intergalactic space as accelerating expansion carries them beyond gravitational reach. Our flow toward Virgo continues, but the Virgo cluster is also merging internally. Multiple large galaxies collide and combine. The cluster becomes more compact and massive. 50 to 100 billion years. This is where things get interesting. Accelerating expansion begins to dominate even on supercluster scales. Galaxies that aren't in gravitationally bound clusters start to drift apart. The space between them expands faster than they can fall together. Laniakea begins to dissolve, not catastrophically, but gradually, as more distant components drift beyond reach. The Virgo cluster, being gravitationally bound, stays together, but its connection to other clusters weakens. The cosmic filaments connecting clusters stretch and thin. Eventually, they dissolve entirely as expansion carries their galaxies beyond each other's gravitational reach. The Great Attractor region, the Norma and Centaurus clusters, will merge into a single massive cluster over these timescales. This bound structure survives as an isolated entity, but its gravitational influence on distant galaxies wanes as expansion carries them beyond its reach. 100+ billion years, Laniakea as a dynamically connected structure ceases to exist. What remains are isolated bound clusters, Milky Way and a few companions, the merged Virgo cluster, the merged Great Attractor cluster, perhaps a dozen others. These clusters are separated by ever-growing voids as expansion continues. Most galaxies outside these bound clusters find themselves in empty space, carried beyond the reach of any major gravitational attractor. Trillion years. Most galaxies we currently see will have vanished. Beyond Milky Way's cosmic event horizon, light from them will be so redshifted that it's undetectable. The observable universe from Milky Way's perspective will contain only the local group's merged remnant and perhaps a few very nearby galaxies. Future astronomers, if they exist in Milky Way, will look out and see mostly empty space. They won't see the cosmic web, won't see distant clusters, won't know about Laniakea. All evidence of the larger universe will have accelerated beyond their ability to observe. Chapter 6.4. The Lonely Future. Cosmic isolation. This leads to a profound and somewhat melancholy conclusion. We're living in a special time. Right now, 13.8 billion years after the Big Bang, the universe is old enough that interesting structures have formed: galaxies, clusters, superclusters. But it's young enough that we can still observe these structures. Before expansion carries them beyond our reach, we can map the cosmic web, study the Great Attractor, understand our place in Laniakea, measure flows toward Shapley and other distant structures. But this window is temporary. A trillion years from now, the observable universe will appear almost empty from any given location. Isolated galaxy clusters floating in expanding voids, with no visible evidence of the cosmic web or larger structures. Future civilizations will face an epistemic nightmare. They'll deduce correctly that they live in an isolated cluster surrounded by empty space. They'll have no way to know about the cosmic web, about superclusters, about the universe's history of structure formation. Their observations will be consistent with a much simpler universe, just their cluster and empty space. They won't know they're missing most of the story. In fact, some cosmologists have speculated that we might already be in a similar situation. Maybe there are structures beyond our cosmic horizon, beyond the region we can observe, that we'll never know about because they've accelerated beyond our reach. This is called the horizon problem in cosmology. The observable universe has a finite size 93 billion light-years across, because light has only had 13.8 billion years to reach us. Beyond this horizon, there might be infinite space, infinite galaxies, infinite structure, but we can never observe it. Moreover, as dark energy continues to dominate, our observable universe will actually shrink. Distant galaxies will cross our horizon and disappear. What we can observe will become more limited over time. We're cosmically privileged to live when we do. Future generations will envy us the view. Chapter 6.5. The Wait. Could dark energy change? Everything I've just described assumes dark energy remains constant or nearly constant, that its properties don't change significantly over time. But we don't know that for certain. We don't even know what dark energy is. There are several possibilities. Cosmological constant. This is the simplest model, favored by most cosmologists. Dark energy is a property of space itself, a vacuum energy that's constant in time. Einstein's equations include a term for this, the cosmological constant, though Einstein initially added it for different reasons and later called it his greatest blunder. If dark energy is a cosmological constant, then its density per unit volume is truly constant. As space expands, there's more space, so there's more total dark energy. This drives accelerating expansion forever. In this scenario, everything I described above happens. Laniakea dissolves. The universe becomes increasingly empty. Eventually, 110+ years, even black holes evaporate through Hawking radiation, and the universe reaches maximum entropy heat death. Quintessence, an alternative model where dark energy is a dynamic field called quintessence, whose properties can change over time. If quintessence is gaining strength, expansion will accelerate faster than a cosmological constant predicts. If it's weakening, expansion might someday slow, even reverse. If dark energy weakens significantly, gravity could eventually overcome expansion on large scales. Structures currently flowing apart might reverse direction and flow together. Laniakea might eventually collapse into a single massive cluster, but this seems unlikely. Current observations show no evidence that dark energy is changing, and theoretically, most quintessence models predict it should strengthen, not weaken. Modified gravity. Maybe dark energy doesn't exist at all. Maybe general relativity needs modification on cosmic scales. Various theories of modified gravity try to explain accelerating expansion without invoking dark energy. If one of these theories is correct, future evolution could be very different than standard cosmology predicts. But most modified gravity theories struggle to explain all observations simultaneously, and they often require fine-tuning of parameters. The truth is, we don't know the universe's ultimate fate with certainty. We're extrapolating from current observations using theories that might be incomplete. But based on everything we currently understand, the most likely scenario is heat death and ever-expanding, ever-emptying universe gradually approaching maximum entropy over incomprehensible timescales. Laniakea's dissolution is just one small chapter in that story. End of Part 3. Continued in final file.